All right, good morning. Can you all hear me?
Yeah, good morning.
Okay, good. Um, Sorry for the delay. My computer decided just to do an update at the last minute, and I couldn't stop it. So, um, I so I got in last night very late. Back from my trip, I got in at midnight. So I'm probably won't stay here till 3:30 today. I'll probably stay here till 2. Okay, so if you want to come by today and ask questions, I'll be here till 2 instead of 3:30. Okay. Um, by the way, can you guys see the board okay? I mean, I know I have the stuff in the way, but can you see the writing on the board?
Yeah,
Okay, all right. So we left off last time um, discussing Gauss's law and application Gauss's law to conductors. I want to do a demo, and then I'll do one more example, and then we'll talk about electrical potentials today, so chapter 25. Just some things that are due. The multimeter assignment's due on the 3rd. And by the way, I heard that a lot of you guys had questions for the lab, which was great last Friday. Read chapter 25 by Friday. And exam 2, which will be on chapters 23 through 25 only. I don't know if you can see that because of Van de Graaff. Okay, chapters 23 through 25 only. That will be on October 8th. So we're going to be a little bit ahead, but at least it gives you some time to study for the exam. Okay? And so this Thursday and next Thursday, you can ask all the questions you want during student help hours, all right, regarding this unit. Because by Thursday, I should have covered everything. All right. And then I'll send you a practice test that's, and this is an old one that I've used in the past. So you have that one and the one for the online exam. You can use them both to help study. You'll see that the exams, those two exams are very similar. Just the problems will be maybe a little bit more non-standard on the online one. Okay. Do you have any quick questions? I know you might have questions on the Gauss's law worksheet. I will. I won't have time. I probably won't have time today to answer questions, but there's a couple people who've emailed me about it, and and I apologize I haven't answered your emails because I was out of town. I just wasn't able to get to them. So I'll get to your emails probably by the end of today. Okay.
you'll be in um you'll be in your office for drop-ins after lecture though, right?
Yeah, I'll either. So
Okay.
yeah, when I'm done, I don't know if you're on campus, but if I'm done, once I'm done here, I'm in WIS 105C. I'm just gonna put this stuff away and go into my office, which is in 107A, which is just down the hall. Okay, so I'll be in one of these two rooms. Okay, so last time we talked about Gauss's law. We talked about conductors in equilibrium. So if you have a conductor in equilibrium, the electric field, by definition, has to be 0 inside the conductor. Okay? And any charge that we place on a conductor, we showed must exist on the surface. Additionally, the electric field, due to conductor, because of that charge that's on the surface, has to point perpendicular to the surface, all along the surface. And then the last thing we talked about was that the electric field is greatest where the charge density is greatest, meaning basically at the sharpest point on the conductor. All right. So I'm going to do a demonstration regarding conductors in equilibrium. So, and I think this is going to work okay. This Van de Graaff is not what it used to be. And I got to move this back so I can plug it in. Also, I want to keep it away from my computer because it's not safe for my computer. So hopefully nothing. I did it last Tuesday, so it should be okay. I'm going to get rid of this PowerPoint slide. You can see everything. So I have a Van de Graaff. Oh, and I need something to protect myself with, because I don't like getting shocked. It won't kill me, but I don't like the feeling of getting shocked. So this is the Van de Graaff generator. So if we were doing the labs on campus, you would be playing with this in one of the labs. The property as a charge lab would involve you playing with one of these. One of the people in your lab group would be standing on an insulator and putting their hands on here while this gets charged up. You know, somebody with long hair. And that would have been one of the things you'd be doing. And every once in a while, students get shocked, but this doesn't kill you. It's just annoying. So anyway, I have this Van de Graaff generator. This thing will charge up to a high voltage. And just to give you an idea, actually, it's not going to work unless I take that off. You can produce nice arcs. I'll show you at the end. I have a wire connected to here. This thing gets charged up. I have a wire connected to here, so I have it also connected to this cage. This is called a Faraday cage. And inside the cage, or around the cage, there are 3 balls. Can you see the 3 balls? Maybe I should zoom in. Give me a second here.
From our perspective, it looks like one is in the middle of the cage. Is that behind?
It's in the middle. You're right. So there's one in the middle. So there's a middle cage, an outer cage. And so there's a ball in the middle, in the inside cage, then one in between the 2 cages and one on the outside. Everybody see that?
Yeah.
Okay.
Fine.
So I'm going to charge this up. And I've connected the wire to the inside cage. And according to what we talked about, if I charge this up, all the charge is going to reside on this surface. And if all the charge resides on the surface, then this ball that's in between the 2 cages is going to feel the effect of this charge. The ball inside won't feel anything, because all the charge is going to exist on the outside of the conductor. And this guy over here is not going to feel anything either. And you can see the ball inside and in between is feeling the effect of this charged cage. But the one inside is unaffected. The one out here is kind of getting affected. That's because I can hear this thing getting charged. And the reason why is there's a conductor here which allows me to connect the outer cage to the inner cage. And I can hear it arcing. Okay, they're not really well isolated, so there is some charge going onto here. That's why this thing is moving out. And you can see a charged object is always attracted to an uncharged object. Okay. And I got to discharge it now before I get zapped. So this is how I discharge it. Okay, there wasn't much charge left, I guess. Now what I'm going to do is connect this cable to the outside. And so when I do that, all the charge is going to exist on the outer surface. Doesn't mean no field inside at all, because all the charge will be in the outer surface. So the ball inside the small cage and the ball that's in between the 2 cages won't feel anything. Only the one on the outside. So you can see the one in the middle is not being affected at all, because all the charge goes on the outside. Because a conductor in electrostatic equilibrium, all the charge is on the outside. No field inside. There's no charge inside. Although I still hear arcing, so there's probably some arcing happening into this thing. Although it actually doesn't matter in this case. Let me show you. I'm going to actually take a wire. I got to find the wire. And I'm going to connect the inner cage to the outer cage. And the question is, what's going to happen? Well, I'm charging both cages. If I, uh-oh. Let's do it this way. If I connect them together, now both the inside cage and the outside cage essentially become one conductor, because electrons could go between the two conductors. And what's going to happen is, even though I'm charging the inner conductor, all the charge in the inner conductor is going to go to the outside. And so the only ball that's going to be affected is this outside one. This middle one's not going to be affected at all. Well, this is how shielding works. So when you're in a thunderstorm, if you're in a thunderstorm, it's actually good to be in the car. The wheels isolate the car, and if the lightning strikes the car, it's going to hit the metal, and you're protected on the inside. And you see nothing's happening, just this thing's moving. Okay? The inner one's not being affected at all, even though these two are connected to each other. Okay? I can tell my system's leaking charge. All right. So let me go back. I'm going to actually just so that I'm going to connect the inner one again so you can see. That one gets charged. Although the outside one's getting charged, a little bit of charge too, because there's arcing occurring. Okay. So that's how shielding works. So I want to show you how I can produce a nice arc with this thing. Again, I'm going to discharge it just in case, because I don't like getting shocked. Some people don't mind it. Let me take this off. So I'm going to let you hear the crack from the Van de Graaff. Do you hear that? I don't know if you can see do you see the discharge? My monitor on my left is not happy. Okay, so I better stop. I don't want to mess up my monitors. One of my monitors just goes out every time it arcs. Okay, I'm going to do this, probably going to use this one more time today. So that monitor is not going to be happy. All right, let me move this back. And unplug it. And get this stuff out of the way so you can see me. And let me fix the camera. Anyways, that's a very good demonstration of electrostatic shielding. Does that look blurry to you?
Does this look blurry?
The screen look blurry to you?
No, it's fine.
Okay. I don't know, it looks blurry. It kind of looks blurry to me, but okay. All right, so I want to do one more example. This is a fairly long example. This kind of incorporates everything in this chapter. And like I said, this stuff is not easy, I understand. But as you do more problems, you'll get better at it. So I have a solid sphere, that's an insulator, and a conducting sphere. Let's not worry about how I put this together. Okay, just as an example. Experimentally, this would be really tough to do. Okay, so So let's say I have a solid sphere. And it has a total charge 3Q. And its radius is A. And it's uniformly charged. And I have a second sphere. I'll make it a different color. This is a conducting sphere. It's actually a shell with an inner radius and an outer radius. Inner radius B, outer radius C. And let's say before I put this together, I put a charge minus Q on it. What I want to do is determine the electric field everywhere. But before I do that, I got to consider what happens to the charge in this conductor when I assemble this thing. Because this is a conductor. Electrons are free to move on the conductor, right? So what happens when I put this thing in the center? By the way, this doesn't have to be a sphere. I can put a point charge 3Q and you're going to get the same result. In terms of how the charge is distributed on the inside of this thing. But I made it a sphere because then I can calculate electric field inside the sphere. Let's make the problem more fun. Okay. In the conductor, what must the field be?
It's a 0.
0. So we know, we know the answer that the electric field between B and C is going to be 0. It's not going to be 0 on the surface because all the charge, whatever charge is there is going to be on the surface. So anything on the inside, the electric field is going to be 0. And then anything from this surface onward, the field is going to be 0. But how is that possible? How can the charge be 0? I'm sorry, how can the field be 0? Because if I apply Gauss's law in here, let's say I choose a sphere of this radius, and I perform this integral. How do I assure that this integral is 0? Because how much charge is inside there? Don't you see this thing inside the blue sphere? If I see that inside the blue sphere, then how can this be 0? Because E is the field. E is the field right on the surface. Well, this is what happens. This integral has to be 0. Q enclosed has to be 0, especially for the spherical symmetry. Okay? This has to be 0. So how does that happen? Well, if I put 3Q here, guess what happens on the inner surface of the sphere? It's going to draw in negative charge all along the surface of the sphere. How much charge? Minus 3Q. So you'll get minus 3Q all the way around here. Okay, you have minus 3q all the way around here. So minus 3q plus 3q gives you
0.
0. So then we're okay, and that has to happen. Okay, if that doesn't happen, we're in trouble. Okay, now this thing originally had a charge of minus q. So if minus 3q got sucked into the inside, and the total charge is minus q, then on the outer surface, I have to have plus 2q. If you notice the total charge, the plus 3q and the minus q ends up to plus 2q. Okay, so on the outer surface, you end up really with the total charge of the two spheres. The total charge you started with. And that has to happen. And so you have charge on the inner surface, you have charge on the outer surface, and inside you have no net charge. The field is 0 inside the conductor. That has to happen. Otherwise, you won't satisfy this. And you do have a few homework problems that go over this. That's basically related to this problem. So now we can actually solve this problem. Okay, we already know one of the answers. We know it's 0 here. Okay, fine. What I'm going to do is start out here. I'm going to go at some point P. I'll use a different color. Some point P. I want to determine the field there. Well, if I'm standing out there, basically all I see is a charge of 2q. A point charge of 2q. If you don't believe me, use Gauss's law. Draw a sphere that goes all the way out to here. What is the total charge enclosed in that sphere? Well, it's going to be plus 2q. And if you want, you can say, okay, well, the integral of E dot n dA is q enclosed, which is 2q, over epsilon naught. And you know we're going to have spherical symmetry. So that's the electric field for R greater than or equal to C. So let's write that down. I'm going to erase all this stuff up here. Okay. So we know it's that for R greater than C. We know that it's this value in here. Now we want to go between A and B. And there's no charge on the surface. And so we want to look at the electric field. In that range. And again, I can use Gauss's law if I want to, but if I'm outside the sphere, it actually looks like a point charge. I can draw a Gaussian surface of radius r, go through this mechanism again, and get the same thing. And so E ends up being sorry if I wrote that small. The last region is inside here. So I got to draw another Gaussian surface of radius r. But it's inside the red sphere. So I need to know how much charge is inside this blue sphere. And that's going to allow me to figure out the electric field on the surface of that sphere. Well, this is going to be a little different. Right, it's the same process, but it's going to be Q enclosed over epsilon naught. Well, this is going to be the integral of rho dV over epsilon naught. Now, this thing is uniformly charged, which means rho is 3Q over the volume of the sphere. If you think about it, the charge inside is going to depend on the ratio of this radius cubed over the radius of the sphere cubed. That's really what it should depend on. Okay. And then our dV, 4 pi r squared dr. Let's put that into the integral. And you know this is 4 pi r squared. I'll put the rho in later because it becomes kind of messy. All right, so we're going to integrate rho. And here's my problem again. I'm going to integrate from 0 to this value r, and so I got to make these dummy variables. Because I'm integrating it to some arbitrary distance from the center of the sphere. And so this gives me 4 pi r squared e. This is an easy integral. And so what happens here? The 4 pi's cancel. The r squared cancels with, it leaves me an r. And so I'm going to get E equals rho over epsilon naught. And that does, I forgot the 3. So it's linear. Okay, it's linearly dependent on r. And so if I put in what rho is, oops. Let's see, there's a lot of 3's here. What do I get? Hold on a second. I forgot my a cubed. You can write it like this. K times 3q over a cubed times r. So you can write it that way because 1 over 4 pi epsilon naught is k. And so I can write E like this. And notice when R equals A, here and R equals A here, the fields match. And they do because there's no charge on the surface of the sphere. Questions on that?
Yeah, I have a question, Professor.
Yeah.
How did you get the density for P? How did you get that again?
I'm sorry, I can't hear you.
Sorry about that. Can you hear me now?
Yeah, a little bit better.
I was wondering how you got the density, the P, which is like the 3 cube or 4/3 pi 8.
Well, if the charge is distributed uniformly then throughout the volume, then it should be true that the density is the total charge divided by the total volume.
Okay, gotcha. Thank you.
Okay, just like when you're talking about the mass density, right? If the mass density of a piece of copper is its mass divided by its volume, and we can say that because the mass is distributed uniformly throughout the volume. So I use the same idea. Okay. Other questions? So I got to graph this though. So let me graph this.
Could I ask before you erase that section?
Okay.
Your bounds are 0 to R, right?
It goes from 0 to R, yeah, because
Okay.
you're trying to find how much charge is inside this sphere of radius R.
Alrighty, thank you.
Okay. So I don't want to erase that yet because I got to make a graph of the electric field here and R here. So from 0 to A, it's linear. It linearly depends on R because this is a constant times R. So it looks like this. And this is R equals A. Then it drops off as 1 over R squared from here to here. Okay, from A to B. So let's say it drops off to about here. And this will be an open circle. And then inside, that's a closed circle. I mean, that one's a closed circle. And then from R equals B to R equals C, the field is 0. And this is an open circle. And then jumps up to here, drops off as 1 over R squared. That's a closed circle. That's what the field looks like if you plotted it. Okay. Now, in the homework for chapter 25, there's a problem related to this. So you need to know how to calculate this field because in chapter 25, you're going to calculate the electrical potential for a system just like this. So you need to be able to find the field everywhere first, and then you got to integrate the fields everywhere to get the electric potential. So you need to understand how to do this problem in order for you to do the problem, one of the last homework problems in chapter 25. Okay. So doing these problems over and over hopefully will help you to better grasp the concepts. Okay, so that's the last item I'm going to cover in this chapter. And so now we're going to move on to the new chapter, chapter 25. And it introduces another topic that's supposed to make problem solving easier, even though it doesn't look like it at first. Okay, because it's abstract. All right, let me. Close one window. Okay, so chapter 25 is the last chapter in this unit, and it's a very important chapter because we're going to talk about electrical potential, which is where the idea of voltage comes from when we talked about the ohms, the multimeter quiz. The idea comes from here. Okay, so I did define it when I talked about the multimeter quiz. I'm going to do it again here. Giving you a little bit more background. Hopefully that'll make more sense. Okay, but again, this is an abstract topic. It is a topic that you can introduce in Physics 205. Normally one doesn't because the usefulness of this concept is not the same as it is in this course. So you can talk about a gravitational potential. I mean, you guys talked about gravitational potential energy. If you define the gravitational potential energy per unit charge, that's called gravitational potential. But usually you don't have time to talk about it in 205, and it really doesn't have as much use. By the way, there is a Gauss's law for gravity too, but we don't talk about it as much. Okay. So I want to start talking about the nature of the electrostatic force. The electrostatic force, the nature of it, depends on 1 over r squared. Just like the gravitational force. It mathematically has the same characteristic. And if you wanted to find the work done by either an electric force or a gravitational force, you know that you have to integrate the force from A to B. Right, that'll give you the work done by the field. It doesn't matter where you bring it. Here's point A, here's point B, and this is an arbitrary path between A and B. If you have an electrostatic force or a gravitational force, it turns out that the integral is independent of the path. So for gravity, and I'll just say Coulomb force, okay, the integral and that's because the force is some function of the distance between the two objects squared. It's some function of the magnitude of the vector r. And it's in the r hat direction. And because of that, the integral is only dependent on the beginning, the location of the first point and the second point. It doesn't depend on the path. This force that we're talking about has a special name. Any force that depends on 1 over the magnitude of r squared, 1 over the magnitude of r cubed, etc., and are in the radial direction, I mean along the line joining the particles. Those are called central forces. The integral only depends on the endpoint, so that the integral is independent of the path. So if you integrate over a closed path, that means closed path, it's always equal to 0. You learned that for gravity, and that's true for the electric field. Okay? So this is true for gravity or the electric field. And if that's the case, you can define a potential energy. So just like gravity, we can define a potential energy for this force, this 1 over r squared force. Oops. I messed up. Hold on a second. Oh, there it is. And so we're going to use the same definition for potential energy as you used in Physics 205. The potential energy, or the change in potential energy, is minus the work done by the field. And I'm sorry, I used dr in my up here, but I used ds in my notes. And the electric field is q times the force due to the electric field is q times E. And this is between points A and points B. So the change in potential energy is minus the work done by the field. The change in potential energy is minus the work done by the conservative force. That's what you learned in Physics 205. Okay, that's a general statement. Work done by a conservative force is always defined as minus delta U. Okay? And this is the work done by the field. Same idea here. So here's a marker I put on the table. If I lift a marker from the table to up here, the work done by the gravitational field is negative. Right? Because the displacement's up, the gravitational field is down. The angle between those two vectors is 180 degrees. The dot product of two vectors that are 180 degrees apart is negative. So the work done by the electric field is, the work done by the gravitational field is negative. But what happened to the potential energy when I lift the object from the table to up here? What happened to potential energy?
It increases.
It increased. And the reason why it increased is because an external force, me, did the work to increase the potential energy. So the work that I did to raise this thing increased the potential energy. Okay. If I raise this up so that the change in kinetic energy is 0, then the work that I did is equal and opposite to the work done by gravity. And so we can say that this is equal to W applied. I'm going to skip the video just because of the copyright problems. Okay, so let's write down our definition for potential energy. Delta U is minus Q. I'm going to assume we're dealing with point charges, okay, not charge distributions, because otherwise it becomes complicated. And again, I apologize for writing down R instead of S here. This is minus the work done by the field. I want to introduce another topic. And I want to look at the potential energy per unit charge. Just like potential energy, this thing is a scalar product. And I'm going to call it delta V. I'm going to say delta V is called the electrical potential difference, sorry. So delta V is the electrical potential difference between 2 points in space. Okay? Energy is the potential energy per unit charge. V by itself is called the electrical potential. So we're going to say V is the electrical potential. And it has units of joules per coulomb, which is the volt. And notice that the volt here is the electric field times the displacement. So the electric field then can be written as the volts per unit, well, volts per distance, volts per meter. Okay, so that's another way to write the electric field. Okay, the electrical potential energy per unit charge is called the volt, joules per coulomb. And the thing is, I also want to reiterate that delta V is the work per unit charge that one has to do, an external force has to do to move an object between points A and B. Since this is W applied, then delta V is W applied over Q. The work per unit charge an external system has to do to move a charge between points A and B. That's what the battery does. Okay? The battery is external to the system, basically. So, external to the wire. And so it's the device that does the work per unit charge to change the potential energy of the electrons in the wire. Okay. So we can say that W applied, I know there's a lot of equations here. W applied is Q delta V, and the work done by the field is minus Q delta V. And I go over this because it's actually important for you guys to know the difference between the work done by some external force and the work done by the field. Now, suppose the electric field is constant. Let's look at this. Actually, let's look at this. And let's look at the special case when the electric field is constant. And that's a bad, again, I got to change that wording, uniform. Okay? It's uniform and constant. So the work done by the field is going to be the integral Q times E times L dot dr. Let's pretend that the angle between E and dr is 0. Let's pretend that E has the same value over the path we chose. And that we'll call the distance between A and B D. And that's the work done by the field, which is minus delta U. Which is minus Q delta V. Look at this and look at this. It's going to give you, if you look at these two terms, Q's, the Q's cancel. And I get minus delta V equals E times D. Let me erase this. Let me solve this for E. This tells me something interesting, that the electric field, if this is going to be positive, then delta V has to be negative. That means that E is directed towards decreasing V. Okay. The electric field is directed towards decreasing V. Okay. So if you know the direction of the electric field, you know the direction of the decreasing potential. That's what that minus sign is. Okay. So I've said a lot of theoretical stuff. Let's see if we can do an example, a conceptual example. Suppose we have a proton moving in the direction of the electric field. So let me write down some equations because I've written down a lot of stuff. And when I ask this question, I always have to derive the answer. I can't remember the answer. I'll never remember the answer. I ask this question because it's always been confusing to me, so I try to derive the answer. Okay. All right. So we have a proton moving that way, and it's moving in the direction of the electric field. So let's say the electric field points this way too. Okay, so the electron's moving, or the proton's moving in the direction of the electric field. Do you remember conservation of energy? What is delta U plus delta K equal to?
0?
0, okay. And so delta U is minus delta K, right? Correct? For a system in which energy is conserved, mechanical energy is conserved. Well, just energy in general. All right, let me just say, let me rephrase that, mechanical or electrical energy. What's going to happen to the proton in its field? Is it going to speed up or slow down?
My intuition is that that's going to speed up.
Right, it's going to speed up because the force is Q times E equals MA. A is Q Q E over m. So this thing is going to accelerate. The acceleration is in the direction of the velocity vector. And so this thing is going to speed up. So what does that mean about the kinetic energy? If it speeds up, what happens to kinetic energy?
It goes up.
It goes up. Okay. Let me put this on the other side. So if this goes up, then what happens to delta U? What happens to U?
It has to decrease, right?
It has to decrease. So kinetic energy increases. Delta K greater than 0. So delta U less than 0. So analogy to that, let me take this marker and drop it. What happens when it falls? Its potential energy decreases because it speeds up. Same idea. So delta U is less than 0. What about delta V? Well, delta V is delta U over Q. If delta U is negative and you have a proton, doesn't that mean that delta V is less than 0? The answer is yes. Okay. And so the proton is moving in the direction of decreasing potential. It's moving along the electric field, and the electric field is pointing towards decreasing V. Now, let's replace this with an electron. Let's do the electron. What's going to happen to the electron?
Is it going to decelerate?
Yeah, it's going to slow down. If it slows down, then delta K is less than 0. And then delta U has to be bigger than 0, right? Now what about delta V? This is a tricky one. Well, if this is bigger than 0 and this is less than 0, then this has to be less than 0. And that makes sense because the electron is moving in the direction of the field. The electric field is pointed in the direction of decreasing V. There's two other cases you can do. You can do the proton moving against the field, and then you can do the electron moving in the direction of the field. Okay. I'm not going to go through every case, but it's worth it for you to do that so that you understand the interplay between delta U, delta V, and delta K. If an electron speeds up, its potential energy will decrease. Anything that speeds up, its potential energy will decrease, because you learned this from Physics 205. Okay? Anything that speeds up, its potential energy has to decrease. If a proton is speeding up, then since this is less than 0, this is going to be less than 0. If an electron is speeding up, if this is less than 0, this has to be greater than 0 because Q is negative. The electron moves against the field. The electron wants to move against the field. So it moves in the direction of increasing potential. Okay? If it's speeding up. Does that make sense? If you go through and try to understand these different scenarios, it really helps you to understand the concept. So we want to find the speed of a proton that's accelerated through a potential of 120 volts. I'm going to leave these equations. Okay. I want to find the speed of a proton that's accelerated through a potential difference of 120 volts. Is that positive or negative? Well, let's see. It's going to speed up, so delta K. We know that from conservation of energy. That's going to give you minus Q delta V. Let's say it started from rest. So then if I solve this for V final, what do I get? If Q is positive, what must delta V be? What must delta V be in order for me to be able to do this problem?
Negative.
It's got to be negative. In fact, I just asked that question a few minutes ago, right? This has to be negative because otherwise you're not going to be able to solve this, right? The proton is potential energy is decreasing, and then since this is negative and this is positive, this has to be negative. I just said potential difference of 120, but I didn't really say whether that's positive or negative. I really made it ambiguous. So what does this come out to be? 1.5 times 10 to the fifth meters per second. I want to show you something about units. If I want to calculate the kinetic energy of this thing, all right, I would take, I basically would take 1.6 times 10 to the minus 19 coulombs times 120 volts. And that'll give me joules. Okay? If I define the electron volt as 1.6 times 10 to the minus 19th joules per electron volt, then this becomes 120 electron volts. We're at the minus sign there, sorry. So this is the kinetic energy, right? Because delta U is, minus delta U is a change in kinetic energy. This is the kinetic energy in electron volts. It's kind of convenient to use 1.6 times 10 to the minus 19 joules per electron volts for the conversion. You guys see that? So if I accelerate an electron through 120 volt potential difference, its kinetic energy is going to be 120 electron volts. It's a very convenient unit to use. Now let's do the electron. So let's repeat our calculation for the electron. What's going to change here for the electron? Well, the mass will change. What else is going to change?
Would the
This
Q be
becomes
negative instead of delta V? Yeah.
I'm sorry?
No, I was asking if the Q would be negative instead of the delta V, but you answered that.
But you're right about that, right? Because this has to be the charged electron is negative, but you're right. It's you have to increase the potential energy. It has to go in the direction of increasing V if it's going to speed up. That's true what you said, and it's going to be I don't have the value, but it's going to be about 40 times larger. Okay, it's going to be about, because the electron is about 1/2000th of the mass of the proton, so the speed would be about 40 times what I had on the board. So I want to, at least, we're getting towards the end, but I want to talk about, since we know a little bit about the potential, can we talk about the electrical potential due to a point charge? So I want to derive an equation for electrical potential due to a point charge. And really I'm going to use this. I'm going to use this defining equation. Find electrical potential due to a point charge. I mean, we know the electric field due to a point charge. Okay. E due to a point charge is K Q over R squared R hat. Or out of simplicity, I can just write it like this. So I don't have to make it that fancy. Okay? That's the electric field due to a point charge. Because I want to integrate this. Now, if I could choose any arbitrary dr. So if this is the r hat direction, then this is, we'll call the theta hat direction. I think you learned that in Physics 205, right? In Physics 205, you talked about the theta hat direction. It's perpendicular to the r hat direction. It's polar coordinates, okay? So your dr will have an r hat component and a theta hat component. Well, if you take the r hat component and dot it with the theta hat component, what do you get? They're perpendicular to each other. If you take the dot product,
Zero.
it's zero. So only the r hat component's really going to contribute. And so, and the r hat's in the r direction. So basically, oops, it's going to give you the following. I forgot the minus sign. It's going to give you that. And that's an easy integral for us to do. Okay, for us we can do that integral. What are we going to get? We're going to get KQ over R evaluated from A to B. Well, let me be more specific. Let me call this R sub A and R sub B. Okay? Instead of just putting A and B. And so that's going to give me K times Q is 1 over R sub B minus 1 over R sub A. Let's say I have a point charge here in space, and I want to know the delta V between some point at infinity and some point here, B, R sub B. Some point B, that's R sub B away from Q. Okay, the other point's at infinity. So let R sub A equal infinity. So I'll put infinity here. This is 0, and so I'm going to get delta V point charge is equal to K Q over R sub B. So delta V, though, is the difference in potential between 2 points. So that's going to be V sub B minus V sub A I'm going to define the V to be 0 at infinity. One of the things that you learn about gravitational potential energy is that you need a reference point to actually calculate the potential or potential energy at a particular point in space. And so I'm going to define the potential at infinity to be 0. And so what that gives me is V sub B is KQ over RB. So in general, we can say that the electrical potential V for a point charge is KQ over R. And knowing that is going to allow us to be able to do a lot of problems. Not every problem, okay, but we can do a lot of problems. And remember that I derived the equation V is KQ over R starting from this. So this assumes point charge. This is only valid for point charges or something I can break it up into a finite distribution of point charges. I can't use this for an infinite plane or anything. But if I have a sphere, I can break up a sphere into a bunch of teeny tiny point charges, and I can integrate over the sphere to get V. And again, this R is the magnitude of the vector that points from the source of the potential to the point at which we're measuring or calculating the potential. So if I have a whole bunch of charges, calculating V is actually very easy. It's a scalar, so it's really easy to calculate V. You shouldn't make a mistake on an exam calculating V, especially if you have the equation in front of you. So if I have some point A over here, and I have a charge Q1 here, Q2 here, Q3 here, so we'll call this R1, R2, R3. If I want to calculate the electrical potential at that point, due to these 3 point charges, this is going to be very easy. You just plug in the numbers and you're done. Don't have to worry about components. This has no components. It's just a number. It's going to be positive or negative. Okay? And that's going to give me, V at point A. And again, this assumes V is 0 at infinity. So if you have a whole bunch of charges, you see the equation. If you have a whole bunch of charges, then V sub A is the sum of I equals 1 to however many charges you have. That's it. Just a summation. It's a pretty straightforward calculation. Let me do 2 more things and then I'll stop. Okay, because I know I started a little bit late. If you need to go, you need to go. This is recorded. Okay. Suppose I have 2 charges. Okay. I want to know how much work is required to have these 2 charges that are really far apart and bring them together to some finite distance apart. Basically, I want to know how much work is required to assemble a system of 2 charges. And we're isolated, right? These 2 parts, there's nothing else in our universe. All right, so let's take the first charge and put it here. How much work is required to put that charge here if there's nothing around?
None.
None. So the work that's required to move this charge here is 0. Let's take the second charge that's way far away and let's put it here. So that this distance, we'll name it R12. How much work does it take to put that charge right there? A distance of R12 from Q1. Well, I'm going to go here. I'm going to use this equation and this equation. And again, this is going to be Q delta V. From over here. So the work that I have to do to assemble this is Q delta V. Delta V of what? Well, it's delta V of this guy. Okay, so it's going to be Q2 times the change in potential that this charge will experience when it starts at infinity and ends up over here. So the final potential is going to be R12. The initial potential and what does that give me? This is the work I have to do to assemble the system of charges. But we know that the work that I have to do to assemble a system of charges becomes stored as energy. In the same way as if I take this marker that's on the table and I raise it to this height here. Sorry, that was too high. Okay? I do the amount of work that I do, I'm the external force. I'm applying a force to raise this thing. I raise the potential energy of the system. So the work that I have to do to assemble a system of charges is this, but that's delta U. That's the change in potential energy of the system. But the other thing too is U initial is 0. This is 0 because the potential energy is defined to be 0 at infinity. And so the energy stored, the potential energy, is K Q1 Q2 over R squared. Okay. So potential energy for a system of two charges is just K, Q1, Q2 over the distance between them squared. No, sorry. Over the distance between them, not the distance between them squared. Sorry about that. You can also derive it from integrating the Coulomb force. But I like doing this approach because it's a little bit more physical. One more example. How much energy is required to put together a system of 3 charges? And of course, that's going to be the energy of the system. Well, I did the first 2. Why do I have to start again? Why would I want to start again? Okay. I did the first 2. So I took charge Q1, put it here. I took charge Q2, put it here. Now I want to take the third one. I want to figure out the total amount of energy that's required to assemble a system of 3 charges. So how much work does it take to move the third charge from infinity to this location here? Well, I have to do work against this charge and this charge. In fact, the total change in electrical potential is due to this one and this one. So how much work does it take to bring this third one in? Okay, so to bring that third one in, it's going to be Q3 times delta V for charge 2 plus delta V for charge 1. But this is going to be V at R2, 3. Yeah, I should. Minus V at infinity plus V 1, 3, at 1, 3 minus V at infinity. What's V at infinity?
It's 0.
0, so these are 0. And so it's going to be Q3 times K Q2 over R2, 3 plus K Q1 over R1, 3. So this is going to be K Q2 Q3 R2, 3 plus K Q1 Q3 over R1, 3. So the total is going to be, the total energy, the total amount of work to put all 3 of them together is going to be these 2 plus this. So total work is going to be K Q1 Q2 over R1, 2 plus K Q2 Q3 over R2, 3 plus K Q1 Q3 over R1, 3. I don't want to do 4 of them because I think if you do 4 of them, there's 6 terms.
So the K1, K, Q1, Q2 came from the previous example?
Yeah, this came from the previous example. I didn't want to
Okay.
do that. I didn't want to do that one again. That's okay. Okay. Yeah, so what I said, yeah, so I said, let's just say we had these two. Now, how much more does it take to add the third one? And that's going to give me the total amount of work that's required to assemble this. And that's going to give me the energy stored in the system. Since the particles came from infinity, and this is the work I had to do to assemble them, then this is going to be the potential energy of the system. Now I can write this in general for a lot of charges. You can write it like this. So you can have it, I and you can sum over I and j equals to 1 to n, but then I and j cannot be equal to each other. But you have to put a 1/2 in front. Why? If I write that summation like that, why do I have to put a 1/2 in front? If I blindly write it as a summation, what's that 1/2 for? Well, because if I read it as a summation, if I had a computer calculate that, if I wrote code on a computer, it would calculate this term twice, right? Because a computer can tell the difference. I mean, don't realize 3 and 2 and 2 and 3. If I switch these two around, it's the same thing, right? Computer doesn't know that. So I'm counting terms twice. That's why I have to put the 1/2. If I write it as a summation like this, I'm counting terms twice.
So that's the potential energy. Should that be the negative of the work? Or am I just confused?
This is the work I have to do, not the work done by the field.
I see. Okay.
Yeah. So I'm going to stop here. I went a little bit over. Thank you for staying over. Okay, and then on Wednesday, I'm going to talk about how you calculate these things. And then the last thing will be doing applications. The last thing I talk about will be very important for the next unit. All right? You guys, we're all okay? All right, so I'm going to stop here. And I think either Wednesday or next Monday, I'm going to do another poll. I couldn't do it today. I couldn't do it for today just because of how late I got in. But I'll have you guys do another poll to see where you guys are at. All right? Okay, you guys take care. We'll see you on Wednesday.
Thank you.
Thanks, Professor.
Sure.